So in chapter 4, we take a step back from looking at the solutions of a given problem, and we look at the collection of all solutions to a particular problem, and look at that set and ask, what shape does that set have? So for simple equations like, say, x squared plus y squared equals 1, the collection of solutions, pairs of points x, y, satisfying this equation has a very particular shape, and we recognize that as being a circle. But it turns out that solutions to systems of linear equations also have a shape, but describing it requires a little bit more abstraction. And that's where we get the notion of a vector space. So a vector space is going to be a set of things of some type. So some set with the property that if you take two things from that set and you add them together, then the sum x plus y is going to be an element of that set again. So you can think of, for example, the integers. If you take two integers and you add them together, you get another integer. Or the set of points in the plane. If you take two vectors of length 2 and add them together, you get another vector of length 2. That sort of idea. But in addition to being having sums contained, we also require scalar multiples to be contained. So, for example, if I take any number c and scale x by multiplying it by the scalar c, I should again get something that's back from my set v. So now, in this case, the collection of vectors in the plane, well, that still works. If I take any vector of length 2 and I multiply it by some of my favorite scalars, say 6, I'm still going to have a vector of length 2. It's still going to be a point in the plane. However, if I take an integer and I multiply it by my favorite scalar, which happens to be 0.3, then I get something that's no longer an integer again. So integers would not be closed under scalar multiplication. And so let me define that term. So we break this property of being a vector space, so the addition and the scalar multiplication property, into two pieces. And we say that V is closed under addition if sums are always contained in V. So if x and y being elements of V implies that the sum is an element of V. And we say that V is closed under scalar multiplication if whenever C is a number, a scalar, and x is an element of V, then the product Cx is also an element of V. And so together, we say that V satisfies the closure properties. And then it's a consequence of this that if V satisfies both, so then V is closed under taking linear combinations. So, in other words, that means that if we take any two elements x and y, so this funny little symbol right here means that if I take any two things x and y which are elements of V, so this symbol is elements, this element of C, so that just means x and y are in V. So if x and y are in V, then ax plus by is in V. For any scalars a and b. Okay. And then we have a special word for if one subspace is contained in another, and that's a subspace. So if V is a vector space and U is a subset of V, so in other words, every element of U is inside V as well, so the whole set U is contained inside V. So if V is a vector space and U is contained in V and it's also a vector space, we call it a subspace. And that's the main idea we're going to work with in this chapter. So all of section 4.1 and section 4.2 is about the formal axiomatic definition of a vector space, and it's got like 10 parts and it takes too long, and we're not going to do that. So we're just going to work by examples and with the notion of these closure axioms. One conclusion that we can draw if we know that V is a vector space, so if V is a vector space, and X is some element of V, so suppose X is in V, then by scalar multiplication, we know that minus 1 times X is also going to be in V. And we know that X plus minus X ran out of room. X plus minus X is 0. So if it's closed under addition, then X plus minus X has to be an element of V. So that tells us that 0 is in V. Okay, long story short, any vector space contains 0. Okay, so this is a simple fact, but it's often one of the easiest ways to rule something out as being a vector space. If it doesn't contain, if I give you a set and it doesn't contain 0, you know it's not a vector space. So when we go to check whether or not, to check if V is a vector space, the first thing to do is to check to see if V contains 0, the 0 element, the 0 vector, etc. And then, whoops, pick two things from the set and figure out if the sum of them has to still be in the set. And then if we pick just one thing, is any scalar multiple of it still in the set? So we'll explain all this through examples in the next videos.